hello and welcome back everyone. We're moving on to the worked examples section for unitary and orthogonal maps, which include matrices and operators. And I'm sure there's a little bit of interest in these notions of orthogonal operators. So we're just going to start with some examples of orthogonal operators. I can't really get into too much detail on these objects because they really should be reserved for a graduate course, or maybe if you're spending a lot of time in either quantum mechanics or advanced math as an undergraduate, maybe you'll eventually encounter these, but I'll introduce them anyway so that we can see what maybe a few of them would look like. So with operators, think about infinite dimensional linear maps, basically on functions, since functions are infinite dimensional vectors. And we'll look at two examples right away. So the first example of an orthogonal operator, and in fact this one's also unitary, but we're going to go with the orthogonal operator first. This is called the shift operator. And all it's going to do is it's going to take a function. So it maps let's say it maps a specific function space. We'll call it L2 of R. I can describe what this function space is in a bit. But all it does is it grabs a function of x, and it's going to map it to a function, but it's shifted the input to that function by 1. So instead of going x, it's going to be on x plus 1. And the inverse of the shift operator is probably not too tricky for you to imagine. It's also going from L2 to L2. The inverse, though, just takes a function. Instead of moving x to the right, it moves it to the left, x minus 1. We can see this is the inverse by, well, what is t of t inverse of f? That's going to be t, so f of x. That's t of f of x minus 1, which is f of x plus 1 minus 1, which is just f of x. So you get back to where you started when you use the inverse. Not really much of a surprise. Well, let's see why it's unitary or orthogonal. It is orthogonal or unitary. It kind of depends on if you want to allow complex valued functions or just real valued functions. Since, let's recall what I was saying before, you want a unitary map of an inner product of functions to be f of u inverse on g, or the inner product. Same with orthogonal, right? Do orthogonal on f, g is f orthogonal inverse on g. So we're in a space of functions, and the L2 on R, the R here, let's just describe what L2 of R is. These are the functions. We'll say, for now, let's just go from R to R, and this will give us real valued vectors, so we'll be looking at orthogonal. R to R, for which the integral over all of R of f of x squared dx is finite. So that just means you can integrate once you square the function. I think I probably talked about that earlier this semester a little bit. But let's go ahead and look at these inner products. So we'll just check the first inner product. So we'll take t on f, inner product with g, that's the integral over our domain, t on f of x against g, and let's just say we're working with real functions, so we'll forget about unitary. We'll just be looking at the orthogonal definition here. So we're working on real value functions, and that's our inner product. And we can compute t on f as f of x plus 1 against g of x dx. And I can go ahead and perform a change of variables, or really a u substitution. So let's perform a u substitution, where we're going to let u be x plus 1, which implies that x equals u minus 1, and it also implies that du equals dx. So under that u substitution, we have r, we have f of u, we have g of u, well, replacing x with u minus 1. So it's g of u minus 1 du. And this last term can be rewritten as the integral over r of f of x, or really I'll say f of u, of t inverse of g of u du, right? Because t inverse is what pulls me to x minus 1, or if my variable is u, it pulls me to u minus 1. So there's the t inverse. And what is this? This is just an inner product, right? F. But all of a sudden, t inverse is now on g. And so we verified that the first inner product is equal to the second inner product, which is the one over there. Because we have a chain of equalities, that's why we gain orthogonality here. So that's like a nice little example of a orthogonal operator on a function space. Let's just look at one more example. The operator f, which takes you from L2 of this domain negative pi to pi, and I think you all probably remember this domain. This was the domain of the Fourier series, to little L2 of z. I'll describe what both of these are right now. These are functions that start in this domain minus pi to pi, and they end up in the complex numbers, and they have the property that f of negative pi is equal to f of pi, and they also need to have the property and they are square integrable. So don't worry too much about these. I just want to show everyone that they actually exist. This little L2 on the right, these are sequences. So recall sequence notation n in z, and these sequences satisfy that they are square summable. So we're treating integrability for summability here. So the operator between those two spaces is unitary when defined as, if I take this operator and I act it on a function of x, what I get out of it, I'm going to compute this by the inner product of f of x against e to the I n x. These are the Fourier coefficients from way back. So you can go all the way back to the Fourier series video and verify that these are Fourier coefficients. But because they depend on n, right? So these depend on n. So these really do form a sub n. They form a sequence with n in the integers. That's what I should write here. This is a sequence n in the integer. This operator is called the Fourier series transform, or sometimes just the Fourier transform. And it ends up being unitary. I can't really describe why. It takes a few pages to describe why this is unitary, but I'll just show you really quick. So if you take the inner product of the Fourier transform of f of x, this is really a sequence, right, against another sequence, b sub n, n in z. So this is a sequence because it's the image of this script f. That, of course, is defined as this infinite sum over the integers a sub n, b sub n, with a conjugate, or that's your a sub n there. It turns out that this is going to be equal to the integral of f of x against the conjugate of g of x dx over my interval from minus pi to pi. Technically this needs to be normalized, 1 over 2 pi, so long as, right, this is going to be f of x against a function, and what is that function g? It's bn e to the I n x. That's the Fourier series reconstruction from our Fourier series video. Of the sequence b sub n. So you'd have to go way back to the Fourier series video for even a little bit of this to make sense. But there is a true equality between these two objects, and actually this notion of the equality between the objects has a very fancy name. It's called Parseval's theorem, or sometimes the Plancherel identity. Plancherel identity. So just both of these first cases, you're not going to be tested on any of this. I just wanted to show that these unitary operators totally exist, because in this last case, what is that? This is actually f of x against f inverse of the sequence b of n, right? So this is that case where you're transforming f to the right with an f inverse, because this is the reconstruction. And so I just wanted to show that these unitary operators do exist on infinite dimensional settings. They just really, they don't look the same as the nice way that we like to think about them in matrix form. In matrix form, they really do look very nice, where you're able to just compute this adjoint and then act the matrix adjoint on itself and see whether or not you get the identity. So with that said, let's go into what we actually probably care about for all intents and purposes in this course. And we're just going to kind of handle one exercise here, and it's going to be identify which of the following are unitary or orthogonal. And we're going to have four matrices here. The first one's going to be 1 over root 5, negative 1, 2, 1, 2. The second one is going to be 1 over root 5, negative 1, 2, 2, 1. So it looks a lot like the first one. The third one is going to be 1 over root 2, 1, I, 1, 1. And the fourth one is going to be 1 over root 2, 1, I, 1. So we're just having a question about these four matrices, which are unitary, which are orthogonal. Let's go ahead and find out. Because the first two on the left have only real entries, it can only be classified as orthogonal or not. And the same with the others, because they both have i's in them, they can only be classified as unitary or not. Okay, so to that end, to test if the ones on the left are orthogonal, all we have to do is take m and act it against its adjoint and see what the result is. So m here is 1 over root 5, negative 1, 1, 2, 2. Its adjoint will be 1 over root 5, and I'm swapping over the diagonal, right? So I'm swapping the 1 for the 2 and the 2 for the 1. That's going to give me negative 1, 2, 1, 2. I then compute this, looking at all rows, install columns, and I have a 1/5 up front because I have 2 copies of root 5. My top row against my left column is going to give me 1 plus 1, or 2. My top row against the right column is going to give me negative 2 plus 2 is 0. My bottom row against the left column is going to give me negative 2 plus 2, also known as 0. And then the bottom row against the right column is going to give me 2 squared plus 2 squared, also known as 8. And that's going to end up giving me, when I pass the 1/5 through, 2/5, 0, 0, 8/5. So it's trying really hard to be the identity, but it's not quite, because those would have to be 1. Right? Would have to be 1 to be orthogonal. So we're going to say not orthogonal. Let's try the next real matrix. I'm going to take m against m transpose. 1 over root 5 against the transpose, just as before. I'm swapping the 2 for the 2. Oh, I haven't finished the first part though. I have negative 1, 2, 2, 1, but the transpose, like I just said, I'm swapping the 2 for the 2, so I have 2 and 2, and then a 1 there. And then I'm going to compute all inner products here. And when I look at I have a 1/5 on both terms. So that's going to give me a 1/5 overall, or 1 over root 5 on both terms. If I look at the top against the left, I have a positive 1 plus 4. That gives me 5. If I look at the top against the right, I have a negative 2 plus 2. That gives me a 0. If I look at the bottom against the left, I have negative 2 plus 2, which gives me a 0. And the bottom against the right, I have a 4 plus 1, gives me 5. And when I pass 1/5 to the inside, I do end up with 1, 0, 0, 1. And so because I have the identity matrix, this is orthogonal. Moving on to the complex matrices on the right, I'm going to try to classify these as unitary. So I'm going to compute the matrix against its Hermitian adjoint with the dagger. So the matrix itself is 1 over root 2, 1, 1, I, 1. The Hermitian adjoint is going to be the transpose, and then a conjugate. So let's just go ahead and write the transpose first. The transpose would be 1, I, 1, 1. But if I'm adding a conjugate, that means I have to put a minus I there. Now I'm going to multiply all rows against all columns. And that's going to leave me with 1/2. Top row against the left column is a 2. Top row against the right column will give me 1 minus I. The bottom row against the left column will give me 1 plus I. And the bottom row against the far right column will give me negative I squared, also known as positive 1 plus 1, will give me a 2, and I'm left with a 1 and a 1, just like I would want, but I have 1 minus I over 2 and 1 plus I over 2. So unfortunately, because those are not 0, these would have to be 0 to give unitary. So they're not 0, so I am not unitary. In the last case, let's try one more time. M times M adjoint, which is going to be 1 over root 2, 1, I, 1, times its adjoint, which is 1 over root 2. I'm taking the transpose, so I'm swapping the two i's around, and then I'm doing a conjugate. So the two i's swap, and I get 1 I, and 1. But then I take a conjugate, so I put a minus sign and a minus sign. What is this going to give me? 1/2. I'm going to compute all rows against all columns, rows, columns. It's going to give me 1 times, if I'm looking at the top row in the left column, 1 times 1 plus negative I squared is 1 minus negative 1, also known as 2. I have 1 I times negative I1, so that's a negative I plus an I. That gives me a 0 because they cancel. If I'm looking at the top left, or the bottom left, I have a negative I, and I have an I, so that gives me a 0. If I'm looking at the bottom right, that's negative I squared, also known as positive 1, plus 1, also known as 2. So this is going to give me 1, 0, 0, 1, which is in fact the identity matrix through and through. And so I am unitary. So we're going to stop there because there's not really too much more to talk about. These are basically the problems you're going to have at hand when you're tested on this idea of orthogonal and unitary, as well as some cool examples that you will not be tested on, but are really fun to keep in mind just in case you ever have questions about those. Anyway, I'll see you in the next class where we're talking about Hermitian and symmetric matrices. See you then. Bye.